All right, let's talk about a chemical transformation that happens in kitchens all over the world. You know that moment when a good bottle of wine gets left open a little too long and becomes, well, something else entirely. This is the story of how that happens, the story of alcohols and acids. So here's our game plan. We're going to start with that classic wine to vinegar mystery. Then we'll get properly introduced to the two chemical families at the center of it all. We'll even check out how alcohol is brewed in the first place and its other life as a powerful fuel. Then we get to the real drama, what I'm calling the great chemical switch, which will lead us straight to the fascinating family of acids. Let's jump right in.
Okay, let's get into it.
Has this ever happened to you? You pop open a bottle of wine, have a glass, and then maybe forget about it on the counter. You come back a week later and, that beautiful aroma is gone. Instead, you're hit with this sharp, super sour smell. So what in the world is going on here? Is it magic? No, it's pure chemistry. You can think of this whole process as a story with two main characters. In one corner, we have the alcohols, specifically the ethanol that gives wine its, kick. And in the other corner, we have the carboxylic acids. They're the ones responsible for that signature sour punch of vinegar. So let's get properly introduced to our first main character, the star of the show when it comes to wine, the alcohol family. Now, in the world of chemistry, a family has a fancier name, a homologous series. But honestly, the family analogy is perfect. I mean, think about it. People in a family often share a last name, maybe they have similar features. They're all related, right? It's the exact same idea here. These chemical compounds are all related because of their structure, which means they act in really similar ways. So what are the family rules? Well, for one, they all follow the same general formula. It's like their secret family recipe. And each member of the family is just a little bit bigger than the last one, always growing by the exact same little building block, a CH2 group. Because of this super predictable pattern, their physical properties, like their boiling point, also change in a really gradual, predictable way. And let me tell you, for chemists, this is a total superpower. It's how we make sense of millions of different compounds. And the real key to their family identity? It's something called a functional group. This is the most important part of the molecule. It's the bit that actually does all the interesting chemical stuff. You can think of it as the family's official ID badge. For any alcohol, that badge is an OH group, which we call a hydroxyl group. See that little OH tacked on? Boom, you're looking at an alcohol. It's that simple. And the cool thing is, because they all stick to that family recipe, we can figure out the formula for any member, no problem. Let's try one. Say decanol. That dec prefix, it's a clue. It means 10, so it has 10 carbon atoms, which means our N is 10. All we do is plug that into the general formula. So 2 times 10 is 20, plus 1 is 21. And just like that, bam, we've got the formula, C10H21OH. See? It's a really neat and powerful system. Okay, so we know what an alcohol is. But how do we even get that ethanol that's in our wine? Well, that takes us to the science of brewing. The whole process is called fermentation. And honestly, at its heart, it's super simple. You've got these tiny little organisms, usually yeast, and they basically just eat sugar, glucose, and as long as there's no oxygen around, they convert it into two things, ethanol, which is what we're after, and carbon dioxide gas. Now, to make this happen, you need 3 key things. First, obviously, you need sugar, like the sugars in grape juice, and some yeast to eat it. Second, and this is absolutely critical, you need an airlock. This little gadget lets all that carbon dioxide gas escape, but, and this is the important part, it doesn't let any oxygen in. And third, you just need a nice, cozy, warm temperature, something around 25 to 35 degrees Celsius, just to keep those little yeast guys happy and productive. The thing is, fermentation alone can only get you so far, usually to about 15% alcohol. After that, the yeast just kind of gives up. So to make the really strong stuff, like vodka or whiskey, you need another step. It's called fractional distillation. It's basically a clever way to separate the ethanol from the water by heating them up. Since they boil at different temperatures, you can collect and concentrate the alcohol. But alcohol isn't just for drinks, not by a long shot. It's also an incredibly powerful fuel. So when you take an alcohol like ethanol and burn it with plenty of oxygen, you get what's called complete combustion. The alcohol and oxygen react, releasing a ton of energy. And the best part, the only things left over are harmless carbon dioxide and water. This clean burn is exactly why we use ethanol as a biofuel in some cars. And we can actually measure how much energy gets released. A classic lab experiment is to burn a little bit of an alcohol, in this case methanol, underneath a beaker of water and just see how hot it gets. So look at these results. By burning just a tiny bit, less than a gram of methanol, the temperature of the water shot up by 21 degrees Celsius. That's a pretty big jump. So that brings up a question. How can you fairly compare different fuels? You need a standard, right? A good way to do it is to calculate the temperature change for every single gram of fuel you burn. Looking at this data, how would you figure that out? It's pretty straightforward, actually. You just take the total change in temperature and divide it by the mass of the fuel that was burnt. And if you do the math, you get 35.6 degrees Celsius per gram. It's this one number that's so powerful. It lets scientists and engineers directly compare the energy bang for your buck of different alcohols, so they can pick the absolute best fuel for whatever they're trying to do. All right, this is it, the climax of our story. We've got our alcohol, we know it can be a great fuel, but what happens when it's not burned, when it's just left sitting out in the open air, like in that bottle of wine we talked about? This, my friends, is the great chemical switch. Instead of that fast, fiery combustion, something much slower happens. The ethanol reacts with oxygen from the air in a process we call oxidation. You can almost imagine the oxygen atoms in the air just attacking the ethanol molecule, pulling it apart, and rearranging it into something completely new. And that new thing? It's ethanoic acid, which, you guessed it, is the main ingredient in vinegar. And you can see the before and after right here. On the left, we've got our good old ethanol with its OH family badge. But after that slow dance with oxygen, look what happens. That group transforms into a COOH group. I mean, look at it. It seems like such a small change on paper, but in the real world, it changes everything about the molecule. Its name, its taste, its entire chemical identity. And just like that, this transformation has introduced us to our second main character. It's time to meet the family of acids. So this new molecule, ethanoic acid, is part of the carboxylic acid family. And guess what? They're also a homologous series, just like the alcohols. They have their own family rules, and their unique family ID badge is that COOH group we just saw. It's that exact bit that gives them their classic sour acidic properties. And to bring it all back, the vinegar sitting in your kitchen cabinet, it's nothing more than a bit of this very acid, ethanoic acid, mixed with water. And there you have it. We've come full circle. We went from the sweet sugar in grapes to the ethanol in wine, all the way to the sour ethanoic acid in vinegar. And the entire journey was driven by just swapping out one tiny piece of a molecule. It really makes you think, doesn't it? If a simple switch from an OH to a COOH can turn a lovely wine into sour vinegar, what other incredible tiny chemical changes are happening all around us, every single day, completely transforming the world as we know it?